Okay. That is either true or false. But most importantly, it can be ambiguous, right? But not both. So those are the three main components of the definition. One, it must declare something, declarative. It must be true or false, and it can be both at the same time. So that's ambiguity by definition. So, examples. The car is red. The door is closed. We are in maths class. These are all prepositions. Notation. Because unlike English again, we don't write a whole sentence for a concept. We usually have a symbol that represents a concept, right? So instead of writing the car is red or the door is closed or we are in maths class, we say prepositions are denoted by common letters. Common Greek letters, our alphabet, right? So, for example, we can say little p. Typically, you will see P, Q, R in the textbook. But why is that? Because P is the first letter of preposition. That's just why. And then they want it to be in alphabetical order, so it's P, Q, R. Or it can be A. So my preposition can be N. Your preposition can be A. Another person's preposition can be little t, right? It doesn't matter, I just call it a letter. And this is how we typically do. They just use colon, which means such that. But it's really just how we define it, how you will always see it. So P, I could say the car is red. Or Q, the door is closed. And anywhere I say P or Q, I know what it means going forward, for example, right? That's the next thing that we need to, before I reach here, my apologies. Before I reach negation. Truth values. And that's it. It's the word that I always check for, because I don't really think it's an English word, but
positive.
Is that English word?
It seems like an English word. That's what it was like.
The truth or falsity of its preposition. Of course, I have to explain what we mean by that, right? So, in our example, we can say, let's say P. We can say we are in maths class. Now, since this statement is in fact truthful, then the truth value is capital T, or T for true, or 1. And physicists would know that 1 typically means on or true, the positive statement. Like if you have a light switch. You ever see a light switch in your house yet? And you see 1 and 0, on and off, right?
You know, instead of 1 and 0, so I think binary.
Yeah, it is binary, right?
Yeah.
So a preposition only has 2 states, by the way, hence binary when we reach that topic, right? Yeah, so the truth or falsity of a preposition, just remember that it can be capital T or 1, that means true, or if we define Q as the AC is off, although this is a lie, the statement is a lie, it is still a preposition. We usually confuse that, and Mr. Kate can confuse it in the exam as well. Giving you something in the exam that is clearly a lie, and you can believe that because the lie can be a preposition. It's a preposition still. All that matters is that I can show that the thing is true or not true, right? So the AC is off. In this case, we can see that the AC is on. So since the AC is actually on, then the statement, the AC is off, is a lie, is false. That's all. Therefore, truth value is capital F for false or 0. Yeah? There is no big deal. Everything that I'm going to be doing today, hopefully you'll scoff at it and say, I know this already. What's he telling me? Fair enough? What's supposed to be logical, right? So, the only thing that is new to you is this term, preposition, or simple statement, right? So, when we have that, we need to be able to define it. It's something that it's a preposition declares something, and it needs to be either true or false, but it can be both at the same time. That's what you need to remember in the definition, right? Did I tell you need another notebook for tomorrow? Yeah, you do need another notebook. You need another notebook for tomorrow as well. You need a separate notebook for tomorrow class, right? Because today is module 1, so we're not going to continue with this tomorrow. We're going to start trigonometry tomorrow. That is module 2. So we're going to be doing module 1 on Saturday, module 2 on Sunday. Right? Cool. And examples, you can see examples, right? The notation, common letters only, Greek letters, we typically use. And then what we call truth value. if the proposition was found to be a truthful statement, they will say we assign capital T for true or 1. Or if it was a lie, can be proven to be true, they will assign a false or a 0. Right? And students typically, when they go in the exam filling out this truth table, they do that. That looks like a T and a F. So don't do that. Thief. Right? And you just get 0. Right? Cool. So even in how you write it, it needs to be clear. That makes sense? May I erase this by the way? And it's not the, no big deal so far, right? Before I go to the negation, I think it is important for us to go through some questions, some more examples, right? So we're going to deal with some examples and some non-examples. Give me some examples of proposition. These are all of propositions, right? And non-examples. Everybody giving me one example and one non-example. I bet it. Let me just ask the question. Okay? Is that a proposition? Did I put it in the right place? You think so? Why would I say that's a proposition? And it can be proven true or false. Right? Suppose I ask, is the AC on? Is that a proposition? But
You can say if it's true or false.
Because you can imagine somebody asking a question, is the AC on and you throw down true? Then just carry the water into one. So, you're not communicating logically. That makes sense? So a question can never be a proposition or a statement. Oh. You see, a question, when I said, is the AC on? Technically, I'm asking somebody to declare to me whether or not the AC was on. Yes, then somebody would respond with a proposition and say, yes, the AC is on. That makes sense? Or no, the AC is not on. That makes sense? So a question don't declare anything. A question asks a question or asks somebody to declare something. Clear? That's important. That's the primary non-example that you'll see in Mr. K. They do ask in a multiple choice question. Fair enough? Alright. I don't know where to put this one. So let me ask. Twice plus 4 equal to 6. Is that a proposition? Hmm?
Yes.
Is it?
Yes.
It's proven.
All right. So what's it declaring? So an equation is indeed a mathematical statement, right? We should know from last time, right? So yes, 2 plus 4 is equal to 6. It's saying if I add any 2 objects to 4 objects, then I get 6 objects in total. That's pretty much what that statement is saying. So yes, equation is always a mathematical statement and it is indeed a proposition. Right? Bear with me, I'm not, you might be bored, but just bear with me. Suppose I ask, remember it's the same equation. Is that a proposition?
No. Yes.
All right. Why say it's not a proposition? Why say it's a proposition?
It's a mathematical statement.
It's a mathematical statement. It can be proven. True?
That is, yeah, once you find a value for that variable, it can determine.
But can it be proven true or false? No.
No, and it is no.
Because they don't know the value of X. Can't be proven now because they don't know the value of X. Hold on.
Yes,
It can be proven. It can be proven.
It can be proven.
It can be proven, sir.
Because it is a
That's
statement.
statement.
Yes,
That's
someone
statement.
says statement.
Yeah, that's statement.
It can be proven.
It's not shown.
Andrew, you guys have a different view than me. Let me hear what you say.
Alright, we don't know the value of X right away. So that's what I'm saying. It can be proven to be true or false.
Because it's depending on the value of x, it can be true. So for example, if I plug 3, if x was 3, then it would have been 3 plus 4 equals 7, it would have been a true statement. If x was 3.
And if x is 4,
But if x was 4, then it would have been 4 plus 4 equals 7.
and that would be false.
And that would have been true in one sense, false in another, ambiguity.
Yeah, exactly.
So that's one reason why it's not a proposition.
It is not.
But what I want you to always remember is that once there is a variable in my equation, it is no longer a statement, it's a question. It is saying, what value of x makes this true? That's what it's really asking, isn't that true?
Okay.
Right?
Yeah, not telling them what's a beautiful topic.
Let's hope you have that view right, right?
I'm going to reach out to the graph.
So x plus 4 equals 7 is not a proposition since it is asking what value of x makes x plus 4 equal to 7. That's really what it's asking. It's always asking to solve x. It's asking something.
Right? This is like asking the question.
It's asking a question in a sense, right? So nothing with variables. So it is clear that x plus y plus z equal to 9. It is clearly not a proposition because there are 3 unknowns, right? That's what we need to find what those are. And remember, it can be true in one case and false in the other, which defies the definition of proposition. That's all. There is no teacher in the class. It is a proposition, but somebody may say it can't be a proposition because that's a lie. There is a teacher in the class.
No, proposition.
That's statement.
True or false.
It no matter, right? So you have to be prepared to defend what you say. You know? I don't need to belabor it. Everybody know what a proposition is, and examples and non-examples, right?
Right.
Here are some examples in the book, quickly. Let's just go through them quickly. Right? Page 3. I'll ask you them, you know. So, when I said, are these propositions? And I said, Port of Spain is the capital of Trinidad. That's a statement. It is declared whether or not Port of Spain was indeed the capital of Trinidad. So that's clearly a proposition. That's all?
Yeah.
And that's the truth value for that would have been T, because it is in fact true, right? All right. But in this class, we always use T and N. I just show you 1 and 0 because sometimes you might see it somewhere. But it won't be in this class, I can guarantee you. Fair enough? All right. Rain is falling. It's a proposition. I can look outside and realize that no rain not fall. So it can be determined to be true or false, and it was declaring something. And the true value for that would be 4 plus 5 equals 12. That equation doesn't make sense, right? It's a lie. But is it a proposition? Still a proposition, right? 17 plus 15 equals 32. Is that a proposition? Yes, by now we know that. And that true value is? No, that true value is T, not true. All right? All right. Example 2. Are these propositions? And you must give reasons, of course. Where are you? Is that a proposition?
No.
Why?
That's a question.
It's a question. Never declare nothing. Full stop. Question don't declare anything. So it's not declarative. 2x plus 3 equals 12. That's a proposition?
No.
No, because it's asking what value of x would make 2 times x plus 3 equal to. Clearly, C is not a proposition either, because that was on the board. What is an even number?
No.
That's a question. It's just asking somebody to declare to them what's an even number. And root 2 is a rational number. That's a proposition. That's the only proposition in all of that, right? All right, see how easy that is? All right, back to the board. Now, when you say negation, what I want you to study is not. Right? So negation means thing is not true. In the English word is negate. So when somebody asks you what's the to negate something, is really to tell the opposite of something, right? Opposite there. So if I were to look at all these and say, all right, the ACs are, what would be the negation of that statement? What would be the opposite of that statement? The AC is?
Not on.
Some people like to talk about exclusive opposites, like use the word off. I just say, anywhere in the sentence, just find a suitable place to put not, right? AC is not on. Fair enough? But off is also accepted in the exam. Fair? So, that's why I said not. Because to write the negation in words in the exam or in the assignment, what is necessary is just for you to put the word not somewhere in the sentence. Fair enough? This one is not really. Right? But how would I write the negation of this? It's interesting.
Draw a line through the equal.
But that would be a
Not
statement.
equal to.
Huh?
Not equal.
Not equal to. So that is making it opposite. Right? That making sense? But we're saying 2 plus 4 is not equal to 6 this time. Good? There is no teacher in the class. What will be the proposition here? Huh?
There's a teacher.
There is a teacher. Not. So you realize that not, because you insert a not right here, and double negative become positive. You remember that?
Okay.
Negative and negative. That's all. That making sense?
Yeah.
All right. Keep that in mind, because it's coming back to hand later on. Is the AC on? Well, that was neither. So we can't do nothing over here, right? That's all. So, symbol or notation. Squiggly is a wave, and I want you to be able to write it. Then start here, you just make a wave. That's all. Okay, so because this was happening very soon, so let's find out. So, in this case, let us say I had labeled these P, Q, R, right? Then, if I say the negation of P, what would that be? What would the negation of P be written as? Squiggly P. Because squiggly is a symbol. And then we have to say symbol with symbol. Fair enough? So that squiggle P means not P. And it is red, not P. Or negation P. Making sense? That would be in symbol. In words, we would say the AC, but squiggly P now would have been the AC is not on. And that's how I would do it. Fair enough? Clearly over here is symbol. And sometimes they'll say write it in words. And you have to be careful because in the exam they will specify if they want it in words or if they want it in symbol. Yeah? So you have to know both. And squiggly R with that same example is the teacher is in the class. Note I don't have much space, but let me tell you what I wrote there. Note, not and no is a double negative, canceling out each other. That's why you know what's in nothing in it and it makes it opposite, right? So later on, you're going to learn, so in particular, in symbol, you will see that squiggly of squiggly P is equal to P. Good? Because not cancels each other. Right, just like when you have negative times negative is positive. That makes sense? Just for information, although you will never see it in this class again, is that negation is sometimes written as negative P, P bar, or squiggly P. They all mean negation, but we stick with the squiggly. Yeah? Let us. What do you think, Randy? If you need to bring a set amount. Can we have another discussion? So, if in this case, P will be, what true value will this be? T, right? And the negation of P would be this. So, the proposition has a true value of T, and the negation has a true value of not T, the opposite of T, right? So, that's the rule for the negation. We're going into that now, right? But before we dive into what truth tables look like, which is in essence what we're trying to do all this time because that's where the marks will be in the exam, right? We have to learn generally about truth tables, right? So let's learn how to construct truth tables. What I put on the board might not be clear until we start putting things into practice, right? So let's go. May I erase all of this? Constructing truth tables. Let me show you what a table looks like. Eh? So we clear. A table has headings. That's all. And then it has rows. Note that I don't usually record the heading with the number of rows, right? So we have to label it. And then we have columns. That's all. Going down. That's all. How many columns? I'm not too sure. How many rows? I don't really know. But that's a table. And these are some of the stuff that we need to consider in constructing a truth table. We need to know how many rows it has, how many columns it has. So that way we know whether or not we have a complete table or we don't have a complete table. Here. So, step 1. Count the number of prepositions. Voila. How do I do that? It is the number of common letters and common letters only. You can call this n. Any number you get is n you call it, right? Step 2. Determine the number of rows. And that's with a formula. Anyone of you three remember the formula?
Which one goes?
We determine the number of rows in our truth table. You ever said that before? No. All right. So it was a gray area. All right. So here is 2 to the power of n. You know indices, eh? What 2 cube mean? A digressing. Yeah, but that's reading it. But what really mean? So it means I multiply that thing by itself how many times?
3 times.
That's what the power tells us. So, alright, good. Remember, everything in mathematics, you come back down to the 4 operations: addition, subtraction, multiplication, division. Right? So all the fancy stuff is just notation and they really mean nothing. You know? Until you put them down to something meaningful. Now here, so in this case, if I were supposed to use an example, because what I'm trying to do is to construct the truth table for negation. I should tell you, right? So you're still leaving space, but below you need to say example. You're still leaving space because we have around 3 more rules, right? The example is construct truth table for negation. So don't write it. When I finish, you just write everything, right? Just watch me for now. So if I was constructing the truth table for negation P, my first step would be what? To count the number of prepositions. How many prepositions I see here?
1.
Well, I see two things there. So how many prepositions? 2. 2 or 1?
2.
You see, you must be saying a question, different answer. Yeah, so you think it's 2 and you change the answer to 2. Andre.
That's good, these are simple and the keys.
You see that? It's specific. Common letters. And squiggly that are common letter. So, alright. So, the number of preposition here, number of preposition which is equal to n is equal to 1. Then I will say, okay, now the number of rows is equal to 1. Hold on. Number of rows, my apologies, is equal to 2 to the n, 2 to the 1 equal to 2. That's all? So this will be whatever that symbol is, right? So now I will know so far that I have 2 rows. So sir, why are you drawing 3 rows? Now one is a heading. What goes in the headings all the time? The prepositions or what you're trying to write true values for. So I know that I have 2 rows. How many columns? Well, I'm not too sure yet. I don't know if I need more columns yet, right? So let's find out what they say about columns. Fill in automatic column. But the hint, each preposition needs a column by itself. So although I am putting in squiggly, constructing the truth table for squiggly P, what is the preposition? So I can't write squiggly P. The leftmost thing is the first thing. Fill in automatic column. Leftmost. So it's the leftmost columns, that is the automatic columns, right? So how many automatic columns I have? Any amount of prepositions I have, I know that the leftmost columns, I need at least that many columns. So if I had P, Q, and R in this statement, that means I would need P, Q, and R. I would need 3 automatic columns to begin with. Here? So in this case, I have only P. So any amount of prepositions I have, if I have 4 P, Q, R, S, I need the 4 columns to start with. Not to end, but to start with a minimum of 4. Fair? And then, how do I complete my automatic column? Because we need to know how to complete the automatic column. Automatic columns has equal number of T's and F's. Let's figure out how to do it, because we write it in English, right? So we have 2 rows in total, right? So here I'm going to say number of rows divided by 2. That's what we always do. Because if I want equal number of something, I would just need to split it in 2, because only T and F it can be, right? So because I would have 2 rows, then this means, what that give you? It means I need to have groups of 1 starting with T. They will always start with T. So in this case, I have 1 T, and then that's a group of 1. Because if I put another T, that will be a group of 2. Right? And it alternates. Okay? Just to believe us. Suppose I had 4. And this was P, right? That means I had like 2 of that. That means I would have had 2 to the 2, 4 rows, right? Then in the first column, it would have been 4. The total number of rows divided by 2, that would have been equal to 2. Then I will say in groups of 2, starting with T, put T's and F. So I've had T, and then T again, that would be a group of 2 now, and then F and F. That's the system we're working with. Fair enough? Then you take this answer and you further divide it by 2. That's the system. Right? This is the hint. When I have group of 1, that tell me that that was the last automatic column. Oh, hold on. This was already group of 1. So that already tells us that this is the only automatic column.
Okay.
That makes sense?
Complete.
Right. So if I had 8, for example, PQR, it would have been 2Q. What's 2Q? 8, right? 2 times 2 is 4 times 2 is 8. So I would have had 4 rows, 8 rows. Then I would have had 8 divided by 2 is 4 in groups of 4. So a 4T, then 4F. Then 4 divided by 2, I would have had groups of 2, right? And then 2 divided by 2 is 1. You see? PQR You see the R automatic column end up with groups of 1. So that's how you ensure that you're correct, right? So in this case now, this should have been groups of 1, T, and then F, and then T, and then F. Here, that's how we fill in our automatic columns, if we have them. Fair enough? So that's the last automatic column. Now, and then step 4. There's one saving grace that most times Mr. K will do this for you and just ask you to complete the truth table. Most times they will fill in the automatic columns. Most times, not all the time. You know? So typically when Mr. K says complete the truth table, this is what you'll have, right? Now, in this case, what we're trying to do is to build piece by piece until we reach what we are trying to get. So because we're constructing a truth table for squiggly P, it means that in the end, a column must have squiggly P, right? Now the thing is, if I never know about P, if I never know about the AC, can I tell you whether that's what's the opposite of the AC? No. So that's why I needed to start with the proposition itself. Now, if I know about P, now I can tell you what is not P. That makes sense? If you never know something, you can't tell you what's the opposite of it. In this case now, it's supposed to be very easy. If P was T, what is not P? The opposite of it. And if P was F, then what is not P? Opposite P. That's how we construct the truth table for negation P. That's it. We're going to get some more examples, right? But just a quick recap to construct a truth table. Any amount of propositions you have, they must start the table, the leftmost column, right? How do I fill them in? In the end, all automatic columns should have, look at this. All automatic columns, look at this, I have 2 automatic columns. How many T's do I have in this one? 2, 1, 2, and then 1, 2, F. How many T's do I have in this one? 1, 2. How many F? 1, 2. You realize all automatic columns end up with having equal numbers of T's in it. But why do I need it in a particular way? Because if I don't have it, if I don't follow my system, then I won't have unique rows. You see? This is the only row that have both this event and that event being true. You see? Yeah, we have, look at this one. We have 1 T and 1 F. Both of them, some people can say, technically that's the same event, but that's not the same event. Because in one case, P is true, and in the other case, P is false. So that's 2 different scenarios. You see? So when I do it like this, 2 things happen. I'm getting all my scenarios, possible scenarios. So I'm exhausting my options, and I can tell you about each of those options. And that is what this truth table is all about. Right? There's an easy way to be logical. So when you're building bridges and building micro sims, when you start work, you can't afford to make mistakes, you know, so you need easy ways to ensure that you consider everything. That's what these things are about. Nothing else. Clear? That's why for you, your electronics, you better know your truth tables comfortably. That's all? All right. But for now, all you need to do is to be able to complete that truth table for Mr. Keith exam. Then you figure it out afterwards. Clear enough? All right. Where can I erase? Oh yeah, you're just right. So give me some time. Any question? You can give him to fill out those truth tables. Right?
Accepted.
Remember this now, because this is not allowing you to construct any and every truth table. Right? That means a cave can possibly give you. Anybody do chemistry in third form? Nope. Everybody's going to the chemistry in third form. So I said third form. Remember what's a compound? Compound usually will test you when you throw two things in it. That make a compound. So what's a compound? Statement. Two things coming together. So in English, you can say the door is open in one compound simple statement. The AC is on is another simple statement. So I can say the door is closed and the AC is on. Or I can say the door is open but the AC is on. I can say the door is closed or the AC is on. All of those things that I use in between are called connectives. Connecting two simple statements to make one compound statement. So, what's a compound statement? A compound statement is a preposition that can be decomposed into two or more simple statements. That's one example. When in doubt, they can say a compound statement is made up or comprised of they're saying the same thing, right? If it's made up of two or more simple statements, I mean it can be decomposed into two or more simple statements, right? What are those examples?
This is on
The door is closed
and
the AC is on. Notice that if I underline that piece, that is one simple statement. And that's another simple statement. Two simple statements. That's all. And then this thing right here is an example, only an example of a connective. What's a connective? Something that is used to join two simple statements. Okay? In English, this is the first difference between your English and your mathematics. In English, we call and or, and but, therefore, are conjunctions. That's all. When you have two sentences, anything that join a word, we call it conjunction. In mathematics, that's not sufficient. Because we can't have multiple things, conceptual things, having the same word conjunction, same name conjunction, right? So you're going to learn that our conjunction is only reserved for your and. We're going to define all of these connectives that we are responsible for. Here. So what are we going to do next week? We're going to deal with types of connectives. In that, we're going to define them. We're going to draw a truth table for them. And we're going to try and use them. What are the types? The first one that we're going to be doing, study the words for next week. The conjunction, which is the simple word for, or the complicated word for and. Right? That symbol is going to look like this. Notice that it almost looks like the intersection set notation. Right? But it's sharp. Upside down V. Right? The two, we're going to talk about disjunction. That is the fancy word for or. And that one is, which is look like this, union. Set notation that usually union mean or all the time. So, you see the similarities? 3. We're going to deal with the implication or the conditional statement. And the symbol here will be like that or that. under implication, we're going to deal with three. Write them now. So when you're reading, you must, when you come next week, you're supposed to know them already because they're all in chapter 1. I'm just telling you what should pop up in your reading, in a sense, right? Under the implication, we're going to talk about the inverse, the converse, and it's not a shoes, and the contrapositive. Then 4, we're going to talk about the double implication. Or the biconditional statement. And that symbol is a double-edged arrow. Or a single arrow, double-edged arrow like that. Conjunction, disjunction, implication, double implication. And you're also going to buck up on something called De Morgan's law. So, at least, at minimum, in your reading, you must have an idea of what those are. Right? You're going to buck up on more things, but that is really sufficient. Right? Right? That's it.
So that's it.
Time class start tomorrow?
So,
What? Oh, so I got almost sure you told somebody want to add something to it. Right?
doing
Unit 2. Moving through.
What time have you to?
Good.
We have some time to get lunch and stuff. Right? I added the